All right, we will continue with the two problems from yesterday that you asked me to cover, which was number 6 and number 8 from the practice problems that were due yesterday. So let's go over number 6 or number 8. Finish going over number 8. Remember, number 8 was the one about the two objects falling from the sky, and we had an elephant and an egg, like I have drawn here. We already went over parts A and B. Part A asked you which object would experience greater air resistance while in free fall, and part B asked you to justify your answer to part A. So we already said that we know that the elephant will experience greater air resistance because it has a greater surface area than the egg. And remember that air resistance depends on surface area, mostly on surface area. Okay, part C wanted you to draw a free body diagram of each object in free fall, determining or showing your answer to part A. So let's do that. Let's erase this. So I have my elephant as my object here and my egg as my, whoa, that was not a very good box. My egg is my object here. We know that both of these are going to have a force of gravity pulling them down towards the earth. And we know that the force of gravity is 9.8 newtons. Well, it depends on the weight, actually, the mass of the objects. So we know that because we just wrote this above, bring this down. It says that I wanted you to draw a free body diagram of each object in free fall showing your answer to part A. So remember, when we're doing these free body diagrams, we care about the magnitude or the size of the vector, the lines that we're drawing in the free body diagrams, as well as the direction. So we know the direction of air resistance will be the opposite of gravity. But what I wanted you to understand is that you should draw a larger air resistance force for the elephant than you should for the egg. So if you drew something like that with the air resistance force, force of air resistance for the elephant, much larger than you did for the egg, you would have gotten points on that if this was a quiz question. All right, and that's all you needed to do for for number 8 of this homework assignment. All right, now number 6, I have written up here, a little girl slides down a hill on a lunch tray. Part A wants to know what type of friction is occurring between the lunch tray and the hill. Well, we have two types of friction that we discussed. We talked about sliding friction and we talked about static friction. Remember that static friction is when the force of friction is equal to the applied force and no motion occurs. It means that there's no net force or that the net force is balanced, right? But that's not the situation here. We're talking about a girl sliding down a hill. We're not talking about a girl sitting on a hill, right? We're talking about her sliding down a hill. So the word sliding itself gives the answer. This is sliding friction. And the reason I know that, sorry, the reason I know that is because there's motion. The net force is unbalanced because there's motion occurring. Part B wanted us to say, was it the net force balanced or unbalanced? Well, it's unbalanced because a motion is occurring. And part C wants us to explain with words and a free body diagram our answer to part B. So draw a free body diagram and explain it, why you said that the net force is balanced in part B. Well, our little sled here, let's actually draw it on a slope. No, we're not going to draw it on a slope. We're going to draw it like this. All right. So the force of gravity is pulling the sled down. We also have a normal force balancing that out. We don't know values for these, so we're just going to write them like that. Okay, then this sled is going down the hill. It's moving. So it has an applied force here. Hold on. let's say that it has an applied force here. The applied force must, because this is sliding friction, must be greater than the friction force, right? We can indicate, if you indicated this with values, if you just assigned values to your forces, that's fine. But you could have also just done it with magnitude. So the force of friction is less than the applied force making the sled go forward. Okay? So something like that, that was enough. And you just explained it the way that I just did. All right, now we are going to move on to section 2.3a, which was about Newton's second law of motion. All right, so we are going to begin going over 2.3a, like I said. So Newton's second law, this is all what A is all about. So Newton's second law states that when an unbalanced force is applied to a mass, the mass accelerates. It can accelerate negatively or positively. Another way of saying this, why I wrote AKA here, is that the acceleration of an object is dependent on two variables. It's dependent on the net force acting on the object and the mass of the object. So, AKA, another way of saying the second law, acceleration of an object depends on two variables. Oops, that's not, yeah, force, mass. Net force and mass. This is the net force being applied to the object. And the mass is the mass of the object. Okay. All right. We're going to look at two scenarios here because Newton's law gives us, it tells us what's happening when there's an unbalanced net force on an object, his second law. His first law tells us what's happening when the forces are balanced. So we have these two different scenarios we need to look at here. When the forces are balanced, what is the acceleration when the forces are balanced? The acceleration is 0 meters per second squared. There's no acceleration when the forces are balanced. This could be when objects are at rest. When an object is at rest, that means that the velocity equals 0 meters per second, right? It's not moving. Velocity is 0 meters per second. So that means that that object will stay at rest. This is just Newton's first law broken down into a diagram. Object will stay at rest as long as the forces remain balanced. As long as the forces remain balanced, that object will stay at rest. Okay, but what about an object that's not at rest? What about an object in motion? Well, we know that velocity here, if an object is in motion, we know that the velocity here is not 0. It does not equal 0 meters per second. It's greater, or it could be less than 0 meters per second. It doesn't equal 0. So as long as the forces remained balanced, remember the reason that this is acceleration, so remember, acceleration is 0 meters per second when the velocity is not changing. So another way of thinking about this is constant velocity, right? Anytime we have a constant velocity, we have no acceleration. Remember, delta V equals 0. That means that when change in velocity is 0, that means that there's no acceleration because acceleration is the change in velocity over time. Okay, so that means that this object will stay in motion. In motion with the same speed and direction with same velocity, right? Like I said, with a constant velocity. Okay, so this is what Newton's first law tells us. This thing broken down, this is just Newton's law broken down kind of into a web, okay? So that's what Newton's first law tells us when the forces are balanced. Newton's second law describes what happens to an object when the forces are unbalanced. Scoot this over here. When the forces are unbalanced, okay? So when the forces are unbalanced on an object, when we have an unbalanced net force on an object, there is acceleration. So here's one big difference between forces being balanced and unbalanced. When we have forces that are balanced, the acceleration doesn't exist. It's 0 meters per second. But when the forces are unbalanced, when there's an unbalanced net force acting on an object, there is acceleration. So we could have the two things that determine what is going to impact the acceleration, whether the acceleration is large or small, is our net force and mass. So acceleration depends directly on net force, F net, and acceleration depends indirectly, but more precisely inversely, depends inversely on mass. All right. So that's what this diagram is telling us what Newton's second law says. So Newton's first law explains what happens to objects that have a balanced force acting on them or not acting on them. And Newton's second law tells us what happens when the forces are unbalanced. So when the forces are unbalanced, there is an acceleration. The object is accelerating. That acceleration could be positive or negative, right? We could be speeding up or slowing down. It doesn't have to be one or the other. I mean, it has to be one or the other. It can't be both, obviously. And the acceleration, whether it's speeding up or slowing down, or how big the acceleration is, or how gradual the acceleration is, that depends directly on net force and inversely on mass. Okay, so let's talk now about that, what I mean by that. We're going to look at the relationship between force and acceleration, and then we're going to look at the relationship between mass and acceleration. So the relationship between net force and acceleration. F net and acceleration, little a. All right, so let's think about this scenario. We have a ball, and I'm two different me's, two clones of Miss Montgomery. I'm going to throw the ball as hard as I possibly can. This space ball. It's the same size ball, same mass ball. I'm going to throw it as hard as I can the first time. And then the second Miss Montgomery, the clone of Miss Montgomery, she's going to just toss the ball very super softly. Okay. So Miss Montgomery, number one, throws the ball with a really big force. Let's say that I throw the ball with a very high speed too, obviously, of 35, hard throw with velocity of 35 meters per second, super hard throw. So this indicates a large force exerted on the ball. I have exerted a large force on the ball. When I exert a large force on the ball, I also exert a greater velocity, or the ball has a greater velocity when it's leaving my hand. Okay? So the biggest thing here More importantly than just a large velocity is going to be a larger change in velocity. Okay, so what I mean by that is if I throw the ball as hard as I possibly can at 35 meters per second, that means as soon as the ball leaves my fingers, it's traveling at 35 meters per second, and then it's going to stop, right? Let's see, if I just throw it out into the grass, it's going to eventually come to a stop. So the initial velocity was 35 meters per second, and the final velocity is 0 meters per second. So my delta V is going to be 35 meters per second, right? Because 35 was my initial, and I'm going to 0. So I have a change in velocity of 35 meters per second. All right, I'm going to put a little asterisk there, come back to this. Let's do the same thing here for Miss Montgomery number 2. She's softly tossing the ball. Soft, that looks like soft. Softly tossing with, let's just say that I have a velocity here of 10 meters per second. Okay, so this is a small force. I'm underhand tossing, just very softly tossing this ball. So I have a small force. That means that when the ball leaves my hand, it has a small initial, I forgot to write that earlier, initial velocity. More importantly, that means that it has a small change in velocity, right? My delta V, if the initial velocity is 10 and the final velocity is 0, my change in velocity is going to be 10 meters per second. Okay, why am I going over all of this? Let's compare these two situations, these two changes in velocity, right? So which of these two has a greater acceleration? Is it Miss Montgomery number 1 throwing the ball super hard, or Miss Montgomery number 2 tossing the ball softly? First of all, this would be a negative acceleration, right? We're slowing down, but that doesn't matter. Remember, acceleration is just change in velocity. We don't care if we're slowing down, speeding up, whatever. So the one with the greater acceleration or deceleration here is the one with the greater change in velocity, because acceleration is a change in velocity and this is over time, remember? So, and either one of these, if we have the same time is not changing, that means that this one has the larger velocity, initial or change in velocity, so therefore it has the larger acceleration or deceleration, right? Okay, what does this have to do with Newton's first law or second law? As the net force increases, when I throw the ball hard, I have a greater acceleration. The reason I have a greater acceleration is because I have a greater change in velocity. Whether that's a positive or negative, it doesn't matter. Okay? When I throw the ball soft or slow, I have a small net force and I have a small acceleration because I have a smaller change in velocity. So from all of this, the takeaway, the important part of all of this is that net force and acceleration are what we call directly proportional. There is a directly proportional relationship between net force and acceleration. So if I doubled my net force, I would double my acceleration as long as I don't change the mass. Okay? So main point, the reason, but you need to understand the why. I'm going to need you to understand that the reason that there is a directly proportional relationship between velocity, or excuse me, net force and acceleration is because this bigger change, when you have a greater net force, you have a greater velocity, initial velocity. Therefore, you have a greater change in velocity if something is slowing down or speeding up, right? Greater change in velocity leads to a greater acceleration because that's what acceleration is, as long as the times remain the same. Okay, so directly proportional relationship. What about between mass and acceleration? Mass and acceleration. Let's think about throwing a ping pong ball that is hollow and has a very small mass, as opposed to a baseball, which has it's solid and it has a lot greater mass. Okay, if we throw these two things as hard as we possibly can, would they have, is that the question I wanted to ask? Which one would go farther? Which one would have the greater speed? If you think about it, when you throw the baseball, it's going to have the greater initial speed, right? It's going to accelerate more quickly than the tiny little ping pong ball, right? So as mass decreases, let's draw this out here. So we have my little ping pong ball. And I'm going to draw that one like that. And then I'm going to draw the baseball as a solid and a little bigger. We're going to say this has a small mass. And the baseball has a large mass. And we're throwing them with the same amount of force. Large mass. This is my baseball. Okay, so what happens to the acceleration here? All right. Let's say, actually, I'm not going to use a baseball because I'm going to make this very exaggerated so it's easier for us to understand. I'm going to say we're going to throw one of those big, huge yoga balls. Have you ever seen one of those? Like the big, massive, I mean, it's humongous. Okay, we're going to throw a big, huge yoga ball instead of a baseball because those two are too close to, it's too hard to imagine that. But I think you could imagine if you tried to throw a big, huge yoga ball with one hand. I mean, that's like the size, I mean, it's massive. I'm pretty sure you've got to have seen one of those before. So we are going to throw a ping pong ball with a tiny little mass, and we're going to throw a yoga ball with a way bigger mass, okay? So think about, just with one hand, we're going to throw these two different objects. With the ping pong ball, I'm going to throw it as hard as I can. I can move that ball a lot faster, right? I can fling it a lot faster. So we're going to have a high acceleration. Let's say that I'm going to have, first we'll do the same thing we did earlier. We'll have a large velocity. Let's say that we have a large velocity of, when it leaves my fingers, it's traveling at 40 meters per second. Okay, and then I'm going to do the same thing with the yoga ball, but I can't move my arm as quickly. I can't apply a force as quickly because that ball is really big. I have to move it from back here and throw it. And even if I push with all my might, it's not going to go with as fast as a velocity as the ping pong ball because I can just move my arm so much faster with that little tiny ping pong ball than I can with this large yoga ball. So I'm going to have a small velocity, initial velocity. I keep forgetting to write initial, sorry. Let's say of 15 meters per second. So which one of these two is going to have the greater change in velocity? Delta V is going to be greater for the ping pong ball because we're going from 40 meters per second to 0 meters per second, which is a change of 40 meters per second. We have delta V on the yoga ball. It's going to be smaller, and the reason for that is because we have a smaller initial velocity. So it's going to be a change of 15 meters per second, from 15 meters per second to 0 meters per second. That's a change of 15 meters per second, right? All right, so which one of these then has the greater acceleration? If we're not changing time, if we're not taking time at looking at time at all, which one of these has the greater acceleration? The small mass, the small ping pong ball, has the greater delta V, right? Has the greater delta V. That means it also has a greater acceleration. The yoga ball has a small change in velocity, therefore it has a small acceleration. So from this information, we can say that the relationship between acceleration and mass is inversely proportional, opposite of what net force and acceleration's relationship is. So mass and acceleration are inversely proportional. That means that as one goes up, the other goes down. So up here in our situation with force and, let me change my color, with force and acceleration up here. As force increases, acceleration increases. As force decreases, acceleration decreases. But when we have that's for a directly proportional relationship, a direct relationship. For an inversely proportional relationship, as mass, let's do it the opposite. As mass decreases, acceleration increases. And as mass increases, acceleration decreases. As one goes up, the other goes down. This is an inversely proportional relationship. All right. What does all of this have to do with anything? This is Newton's second law. We're breaking down Newton's second law. His second law says that acceleration is directly proportional to force and inversely proportional to mass. The equation, we have an equation for Newton's second law. And this equation says that acceleration, A, is equal to F net. Hey, that's a directly proportional relationship, right? Acceleration equals force. Yes, that's exactly what we just found, right? As one goes up, the other goes up. As one goes down, the other one goes down. Perfect. It's equal to net force divided by m, mass. So that means that acceleration is equal to 1 over mass, right? The inverse of mass. As mass increases, acceleration decreases, and vice versa, right? So this is the equation explaining everything we just went over here, explaining those two relationships, that force and acceleration are directly proportional, and mass and acceleration are inversely proportional. This is the equation showing that. Oftentimes, you're going to see this equation written as force equals ma, which it's the same thing, right? Because if I wanted to isolate force on one side, I would just multiply both sides by m, and I would get ma equals net force, right? So you see these written both ways. So if you see it written like that on a problem or in your notes or in the readings or something, don't freak out. It's more common that we see it written actually this way than we see it arranged for acceleration, because that's just the way that it is. Okay. All right. So let's look at, I want you to remember one thing about the units of newtons. Remember that 1 Newton is equal to 1 kilogram times meter per second squared. Sorry, there's a helicopter going by. All right. So that's very important that you remember that. That you keep that in mind, because, and it also makes sense really if you look at the equation. 1 kilogram, well, this is actually for this equation. See, it's relating this one right here. 1 kilogram, kilograms are the unit of mass, right? And acceleration has the units of meters per second squared, and force has the units of newtons, right? So it actually does make sense, but another way of saying 1 Newton is 1 kilogram times meter per second squared, okay? All right, let's look at some example problems here. Okay, I'm gonna write this table up from really quickly. get this up here. Okay, so we have here, we're going to fill out this table. It's going to have 5 rows. So first we have a net force of 10 newtons, N is newtons, 10 newtons, and a mass of 2 kilograms. So for example, an object has let's say Miss Montgomery is pushing a ball with 10 newtons of force, and the ball has a 2 kilogram mass. What is the acceleration of the ball? To solve for that, we would use our equation that we just had above. Force here is, let's write it, A equals F net divided by mass. So that's going to be equal to 10 newtons divided by 2 kilograms, right? So we get here an acceleration of 5 meters per second squared. You might be saying, how the heck do we get meters per second squared from these 2 units, newtons per kilogram? Well, remember that a newton is the same thing as a kilogram times meter per second squared. And since I have kilograms on top, kilograms on bottom, I'm left with meters per second squared. Okay. All right, that's pretty straightforward, pretty simple. Just plug it in and solve, okay? So that is our first row. Next, Miss Montgomery is going to be pushing the ball now with 20 newtons of force. The ball hasn't changed its mass, it's still 2 kilograms. So now what is the acceleration of the ball? Okay, so I'm now pushing the ball with more force, with in fact 2 times the amount of force. So before we fill out this table or do the math to solve it, what do you think is going to happen to the acceleration? Well, hopefully you remember that there's a direct relationship between net force and acceleration. So that means that the acceleration should increase, right? There's a direct relationship between these two. So if we increase force, then acceleration should also increase. And if we plug this in, divided by mass, we find that that is true. 20 newtons divided by 2 kilograms is equal to now an acceleration of 10 meters per second squared. Okay, I'm going to fill out the rest of this table and then we're going to come back and discuss it. But anyway, the next thing, now I'm going to be pushing, rather than pushing a 2 kilogram object, I'm going to be pushing a 4 kilogram object. So now we're going to change the mass, but I'm going to still push it with 20 newtons of force. So now I'm changing the mass of the object. When I change the mass of the object, do you think that the acceleration should go up or go down? We're just going to compare these two here. The acceleration for the 4 kilogram mass, will it be greater than or less than the acceleration for the 2 kilogram mass? Well, remember that there's an inverse relationship between acceleration and mass. Mass is on the bottom. So if I increase the bottom, I'm going to decrease acceleration. So 20 newtons divided, and we can prove this mathematically, that's what I'm doing now. 20 newtons divided by 4 kilograms is going to give us an acceleration of 5 meters per second squared. 5 meters per second squared. So by increasing the mass, I've decreased the acceleration. Let's say that, what if I increased the acceleration to 20 meters per second squared, and I am still using my, well, I'm going to go back to my 2 kilogram mass. So based on everything we have done so far in this table, what do you expect the force to be? Is the force, if we're using, now we're using the 2 kilogram mass again, like we were up here. Okay, what would you expect the force to be? Think about it for a second. Would you expect it to be greater than, less than, or equal to these two that we found earlier? Well, hopefully you say greater than because there's a direct relationship between acceleration and force. How much greater than? Well, if we plug it in, if we solve, we would have F. We're not going to use this equation. We're going to rearrange for force now. So we have F times mass, or excuse me, equals mass times acceleration. We have a 2 kilogram mass times an acceleration of 20 meters per second squared. That gives us a net force of 40 newtons. So I've doubled if I compare this row to this row. The only thing I'm changing is I doubled my acceleration. I went from 10 to 20. When I double my acceleration, I exactly double my force, right? So this is an important, I want you to understand the reason I'm making such a big deal about this is because you really need to understand this relationship, the direct and inverse relationships that are explained in Newton's second law here. Okay. All right. So that is it for, yeah, that's going to be it for today. What you're going to do is answer some second law questions and for the rest of the period. And if you don't finish them, I think you hopefully should be able to finish most of them. It's not that long. If you don't finish them, you will need to finish them for homework for tomorrow. And then for tomorrow, I will be going over 2.3 part B, and there will be no homework tomorrow because on Thursday you have your quiz. So please let me know if you have any questions. Work on this homework assignment, please, in-class assignment, and I will talk to you later. Thanks.